transition metals, there are some exceptions to this whole, what we've been doing, all right? For example, we would expect chromium to be, and this is the shortcut, AR 4S what 3D what? What would you expect it to be? 4S, so we look, all right, and we're looking at it, so it's gonna be 4S what? 4S2, and then 3D what? 4. Okay. But what actually ends up happening is there's a little shift. It has to do with energy, all right, and stability, but mainly like energy. Like these electrons, they want to be in the lowest energy level that they can be in, and they want to be spread out from each other. So what actually happens here is instead of it being 4s2, 3d4, it ends up being 4s1, 3d5. All right, so let's look at what happened first. First, the S moved over, right? One of the S's went over to the D's. Now, just by looking at this, you're like, okay, that's a little odd, but if we draw the orbital diagram for it, it'll make a lot of sense. So let's draw what it looks like first. So we have for the orbital diagram, AR, 4S with 1 line, and then 3D with 5 lines. And you can just draw this anywhere in the margin, all right? Now, originally, it would look like 4S2, 3D4, right? Now, check this out. Where do you think that one electron goes from the S? Yeah. To the last open one in the D to kind of spread everything out, right? So the idea makes a lot of sense that it's spreading out. The reason behind it has to do with energy, all right? And it just likes to do this. There's a lot more technical reasons for this, but if you go into AP Chem or College Chem, they'll talk about it. So what you have is this movement where this 4s electron goes over to the 3d. So it actually jumps to a lower energy level because this is on the 3rd energy level. So what it would look like would be AR 4s1 and then 3d5, like we said before. So they're all up arrows. A neat thing about this is when you have a lot of up arrows like this, that means that whatever this is will be magnetic. So when you think of magnetic objects, they have a lot of these single arrows going in this one direction. All right? Any questions with that? No? Okay. All right, so the S2 loses an electron, becomes S1. The D4 gains that electron, becomes D5. Why? It has to do with the D5 requires less energy than having electrons in both the D and the S paired up. You could say it's more stable. Once you get into higher levels, like I said, they'll talk more about it, all right? But that's kind of the basics for it. Does that make sense? Now, that happens usually whenever you have a D4. So that switch will happen in there. All right, so let's fill this in. It's an exception. When we do the exception, it'll be 4s1, 3d5. This would do the same thing, all right? It would move one over. Unfortunately, there are exceptions to the exceptions, which means this acts normal. So it'll actually be S2, 4F14, 5D4. So it doesn't do that shift. So you're like, how am I going to keep track of this? Well, if you look in that column, what we're talking about is chromium and then 42, MO, right? Those are the two that do this exception. So on that periodic table that we outlined, I would outline those two just so you remember they're exceptions. All right, so just outline chromium and molybdenum. Tungsten and cyborgium don't do it. They just follow the normal rules. All right. Okay, so molybdenum comes up with this krypton 5s1, 4d5 because it does the exception rule, and then these are exceptions to the exception, so they don't do that shift. So you get S2, D4, S2, D4.